Hi, y'all. I am going to record I'm going to make 3 recordings for this module on Greek mathematics after Euclid. We're going to talk about 3 different mathematicians in this particular module. The first one, Archimedes, we've already been talking about. We're going to finish him in this first video. The second one is Eratosthenes, and the third one is the first female mathematician, Hypatia. So I'm just going to post 3 different videos for one for each of those mathematicians. Now remember, we've already been talking about Archimedes, so the last part of the video that's posted on Euclid's Elements actually is our first lecture on Archimedes. So go back to that if you need to kind of get a head start and see what we've been talking about with Archimedes. So I want to do one thing. I've added one thing to the PowerPoint for Archimedes, so I want to show you that. So let me bring that up. And that's where I want to start. This is what I've added to it. It's just the legacy of Archimedes from the current slide. And it's not going to the current slide. Okay, so let me go back to the next to the last slide, the legacy of Archimedes. Just a couple of things I want to make note of. The first one deals with actually this last thing we're going to talk about, which is the first thing. The last thing about Archimedes, which is the first thing I'm going to talk about today. And it has to do with how Archimedes approximated the value of pi, or another way to look at that is how he found the circumference of a circle. So using the method that he did, he ended up with pi would be approximately 22/7, which is equal to 3 1/7. And that's probably the first approximation that we learn in middle school or high school when we're talking about pi. And it is known as the Archimedean value because it's Archimedes who gave us that value. Galileo, a scientist and mathematician in Italy in the 1500s, called him superhuman. So he was so important that Galileo thought that he was just more than a human being. The work that he did was incredible, and he called him a superhuman. And then a little bit later on, in the 1600s to early 1700s, Gottfried Wilhelm Leibniz, who was one of the co-inventors of calculus, he's a German mathematician, wrote, "He who understands Archimedes and Apollonius will admire less the achievements of the foremost men of later times." So even though the mathematicians of his time were doing more advanced mathematics, he recognized that the work that these two did, Archimedes and Apollonius, were at the forefront of mathematics for all time. And there is a crater on the moon, which is known as Archimedes, and there's a mountain range named Montes Archimedes. The exclamation of Eureka, which is what what Archimedes yelled when he jumped out of that bathtub after he had solved the problem of the golden crown, is actually today the state motto of California. And the reason is Eureka means I found it, I found it. So imagine the gold first person who was panning for gold and discovered gold in the hills of California, found it and said, I found it, Eureka, Eureka. So that's their state motto. And then finally, the Fields Medal, which is it's kind of the Nobel Prize for mathematics. There is no Nobel Prize for mathematics. They're giving those out right now, so you'll notice that no mathematician is going to get one unless a mathematician gets one in another field. And that's what John Nash did. He was a mathematician who got the Nobel Prize for economics. But the Fields Medal is for outstanding achievement in mathematics. And on one side of it, it has a portrait of Archimedes. And so you can see his portrait, and then you can see down this inside the outer inscription in Greek is the word Archimedes. So you see the alpha and then the rho and the chi and then so on. There's his name. And then on the other side, there's an illustration of the cylinder and the sphere, and that represents the proof that Archimedes did that relates the surface area and the areas, the volumes of the sphere and the cylinder. And you'd have to cut, it's behind actually that laurel crown and the plaque that's in front of it. You can see the very top of it, you can see the very bottom of it. And this was the inscription that Archimedes wanted to be placed on his tombstone. And it's the one that when Cicero went into Sicily and found his grave, he had a new tombstone made, and that's the inscription that was on his grave. Now, one last thing about Archimedes, and this is really, really, really important in some way, shape, or form will be on that first exam. Archimedes is considered one of the three greatest mathematicians of all times, from zero to now, actually, from negative numbers to now. So it's Archimedes, Isaac Newton, and Carl Friedrich Gauss. Those are the top three of all time. Archimedes, the first one, is also known as the greatest of all ancient mathematicians. There were lots of them, lots of ancient Greek mathematicians. And the Apollonius was one that Leibniz just mentioned. But Archimedes is well known as the greatest of them all. And I said that was the last thing, but just one more thing about Archimedes. Archimedes, we believe, studied in the city of Alexandria when he was a young man and worked with the mathematicians at the time, and then went back to Sicily and continued his life's work. So we're going to talk about connections to Archimedes with the next two mathematicians as well, and several other ones. I mean, the connections with Alexandria. And if you need to, go back and look at one of the maps to see where Alexandria it is. It's on the coast, the Mediterranean coast of Egypt. It's a coastal city named after Alexander the Great. All right, so now let's go back. Let me stop the sharing. And I hope before, if you haven't run off this piece of paper, it's going to be in your Canvas module. Let me show you what it looks like. Okay, if you haven't run this off yet, come on. Let's focus it. There we go. Run that piece of paper off, stop the recording, go make a copy of it so that you can take some notes on it and see what I'm doing as we go along. Okay, I'm going to show you the method that Archimedes used to find the circumference of a circle. This is an application of Eudoxus' method of exhaustion. So the Greek mathematician who came up with the method is Eudoxus. And it may remind you a little bit of calculus. Remember when we first started finding the areas under curves, we looked at inscribed rectangles and circumscribed rectangles, or those rectangles that were part under and part over, and we tried to fill up that area under the curve. We were exhausting the area. Well, that was Eudoxus' method. So this is really an application of that method of calculus that we use to find derivatives, or to evaluate integrals, I should say. All right, there are two formulas that we're going to need to use because Archimedes looked at inscribed polygons. I've got a hexagon drawn right here. Here's the circle, and I want to find its area. I mean, its circumference, I'm sorry. I want to find the circumference of this circle. So the first thing he did was inscribe a hexagon. Okay, we're going to find the perimeter of that hexagon. Then he took the same drawing, but he circumscribed a hexagon, so it's on the outside of the circle. He found its perimeter, and so he knew that the perimeter of the circle, which is its circumference, was between the perimeter of the inscribed polygon and the perimeter of the circumscribed polygon. Okay, that was his first step. Then what he did was doubled the number of sides for each of those polygons. So he got an inscribed dodecagon and an inscribed and a circumscribed dodecagon. And the circumscribed dodecagon is inside the circumscribed hexagon, and the inscribed dodecagon is, and that's 12 sides, is inside the circle, but it's between the circle and the inscribed hexagon. So he's squeezing that perimeter. He's getting closer and closer to it, closer and closer to the circumference with the perimeters of the circumscribed and the inscribed polygons. Okay, and he used a process where at each step he could double the number of sides of the polygon. But to do that, he needed some formulas. So the first is the formula for the perimeter of an inscribed polygon. And that perimeter is little p sub 2n, 2n is the number of sides, equals the square root of little p sub n, in other words, the perimeter of the insided polygon, times capital P, which is the perimeter of the circumscribed polygon with twice the number of sides, 2n. Okay, so that will give me the formula. That's the formula that I need to use to find the perimeter of these inscribed polygons. Well, I need another formula for the perimeter of the circumscribed polygons. So perimeter of circumscribed, I'm writing on my folder, circumscribed polygons. And that is represented with a capital P sub 2n equals, this is a fraction, 2 times little p sub n, so the perimeter of the insided inscribed polygon, times capital P sub n, so that's the corresponding circumscribed polygon, divided by the sum of those two perimeters. The perimeter of the inscribed polygon plus the perimeter of the circumscribed polygon. Okay? But I've got to get started with this with a particular polygon. And he started it with the hexagons. So I'm going to find P sub 6 and capital P sub 6. The perimeter of this hexagon that's inscribed, the perimeter of the hexagon that's circumscribed. And then once I get those two numbers, I can find the corresponding perimeters for 12-sided polygons. Use that, double the number of sides. I can find the perimeters for the 24-sided, and so on, as long as I want to keep that going. Okay? Anytime you need to pause this recording, just pause it. I'm going to keep going. So I need some room down here. So I'm going to fold this and move it up. And I'm going to find the perimeter of the inscribed polygon first. All right, so this is the inscribed hexagon. Hexagon. Okay, well, the first thing we're going to do is we're going to let R, the radius of our circle, R is going to be 1/2. And here's another radius of that circle. So that's 1/2. Well, what I have over here, I know that this is a regular hexagon. So each one of these angles that I would draw, there are 6 of them. They're all the same measure. So this must be a 60-degree angle right here. Since that's a 60-degree angle and this is an isosceles triangle, these two angles are the same measure. They all three add up to 180 degrees, so they are all three 60-degree angles. So I have here an equilateral triangle. And if this side is 1/2 and this side is 1/2, then since it's equilateral, that side is also 1/2. And I'm going to let little s equal the side of that triangle. I'll put dots on the s. Okay, well, the perimeter, little p sub 6, is equal to 6 times the length of the sides. It's a regular hexagon, so all 6 sides are the same length. That side length is 1/2, so they're all 1/2. So P sub 6, the perimeter of the inscribed hexagon, is 6 times 1/2, which is 3. Okay? So I know right now that the circumference of the circle is greater than 3. It's close to 3, though, because that hexagon is pretty close to that circle. It's not quite as big, but close to it. All right? Well, what about our circumscribed hexagon? Okay? And in fact, let me do this. I'm going to use 2 of these triangles, so just to show the difference, which one's which. Let me outline this one in yellow and underline this. There's the perimeter of the yellow triangle. Okay? Now I'm going to come over to the other side and let's see. Here's the side of the circumscribed polygon. So let me draw that polygon. Grab a ruler. Draw in these 2 sides. Okay, now what I want to know is what's the length of each of these sides? And let me color this one in using my orange pen. So all 3 of those sides are the same length. I just want to figure out what they are. Okay, now what I know is that if I were to bisect this vertex angle, okay, bisect that angle, that's a 60-degree angle right there because that's a regular hexagon. So each one of those angles is 1/6 of 360 degrees. So that means that this would be a 30-degree angle because I just bisected it. And when I bisect that angle, I'm going to bisect the opposite side. So this turns out to be, if this is S, this is half that side, S over 2. And that's the radius of the circle. So I know that that side length is 1/2. Now, that side length is the side length of a right triangle. Here's a right triangle. This is only half of the triangle that's part of my circumscribed hexagon. Okay? So with the inscribed hexagon, I just looked at that entire triangle that I drew. But now with the circumscribed, I'm going to bisect that angle and look at that triangle right there, which turns out to be a right triangle. All right, so what I want to do is find the length of S, which is the side length of an equilateral triangle. Okay, so once I know what S is, all I'm going to have to do is multiply that by 6 to get this perimeter. All right, well, this is a right triangle, so I can use the Pythagorean theorem, and I know that the length of this leg squared plus the length of this leg squared is equal to the length of the hypotenuse squared. So I've got the equation 1/2 squared plus S over 2 squared equals S squared, which is the same thing as 1/4 plus S squared over 4 equals S squared. And if I multiply both sides by 4, and I'm writing it out like this, strung out because I'm at the bottom of my sheet of paper, I'll get 4 times 1/4 is 1. 4 times S squared over 4 is S squared. and that's going to be 4s squared. So when I get my s squareds together, I've got the equation 1 equals 3s squared, which means s squared is 1/3, which means the side length s is the square root of 1/3, which is the square root of 3/3. If I rationalize that denominator, I'll get the square root of 3/3. So the perimeter capital P sub 6 is equal to 6 times the square root of 3/3, which is 2 times the square root of 3. And 2 times the square root of 3 is approximately 3.4641. Okay? So what I know is that that circumference is between 3 and 2 times the square root of 3, which is approximately 3.4641. Well, that's close, but it's not all that close. Now, what Euclid and what Archimedes knew was that if he doubled the side length and looked at the inscribed dodecagon and the circumscribed dodecagon, he would get even closer. So that's what we're going to do. We're going to find the perimeters of the inscribed and the circumscribed dodecagons. Perimeters of inscribed and circumscribed dodecagons, and that means 12 sides, a 12-sided polygon. And I should say inscribed and circumscribed regular dodecagons, which means all of the sides are the same length, all of the angles are the same measure. Now I'm going to need to go back to my formulas right there. Okay, so let me write the formula down for the inscribed. I've got P sub 12 equals the square root. All right, so 12 is 2 times 6. So in this case, n is 6. The square root of P sub 6, which is the perimeter of the inscribed, times capital P sub 2 times 6, which is 12. All right, well, now I'm in a pickle because to find the perimeter of the inscribed dodecagon, I need the perimeter of the circumscribed dodecagon. So this isn't the one I'm going to do first. I'm going to find the circumscribed perimeter first. Or I should say the perimeter of the circumscribed dodecagon. So capital P sub 12, this is from this formula, is equal to a fraction, and the numerator is 2 times the perimeter of the n-sided, and in this case, if this is 2n, it must be this hexagon, 6 sides, times, that's the inscribed hexagon, times capital P sub 6, which is the circumscribed hexagon, over the sum of those two numbers, P sub n plus capital P sub n. All right, now remember what we did before. P sub n is equal to 3, and capital P sub n is equal to 2 times the square root of 3. We're going to leave it using square root so that we're going to have accuracy as long as possible, or exact answers as long as possible. Okay, I don't need this anymore because I've already written it down with the values of n that I need to use. Okay, so I'm going to leave the inscribed for a little bit, and I'm going to work on the circumscribed. So capital P sub 12 is equal to 2 times 3 times 2 times the square root of 3 all over 3 plus 2 times the square root of 3. And that's equal to 2 times 3 is 6 times 2 is 12 times the square root of 3 in the numerator over, well, there's no way I can combine those two terms. That's an integer and that's an irrational number, so I have to leave it as 3 plus 2 times the square root of 3. But what I'm going to do is rationalize the denominator. And there's a good, sometimes I wonder what's the purpose of it, but there's a good reason for this one. All right, so I'll multiply 12 over the square root of 3, 12 square root of 3 over 3 plus 2 times the square root of 3 times the fraction 3 minus 2 times the square root of 3 over 3 minus 2 times the square root of 3, because I'm just multiplying by 1. I'm not changing anything. So 12 square root of 3 times 3 is 36 times the square root of 3 minus 12 times 2 is 24. And the square root of 3 times the square root of 3 is 3 all over. Now remember, this is the sum of two numbers times the difference of the same two numbers. So my middle terms are going to subtract out. I'll get minus 6 square root of 3 plus 6 square root of 3. So I've got 3 times 3 is 9 minus 2 times 2 is 4 times the square root of 3 times square root of 3 is 3. Now that's what's nice about rationalizing the denominators, because I'm going to get this nice integer as the denominator. So I've got that's equal to 36 square root of 3 minus 72 over 9 minus 12 is negative 3. So when I divide negative 3 into both of these numbers, I'm going to take the whole number first. Negative 72 over negative 3, plus it's going to come out to be positive. That's 24. And then 36 times the square root of 3 divided by negative 3 is minus 12 times the square root of 3. So that's the perimeter of the circumscribed dodecagon. And that is approximately equal to 3.2154. A little bit closer to what we know as pi. And the reason we're choosing 1/2 is because we know that the circumference of this circle is 2 pi r. And if r is 1/2, 2 times 1/2 is 1. So the circumference of this circle should be pi. Okay? So pi is close to 3.214. It's a little bit too big. I bet this one's going to be a little bit too little. So I've got p sub 12, little p sub 12 is equal to the square root of little p sub 6, which is 3. Oh, I should have put here 6 and 6 as the specific numbers, times the perimeter of the circumscribed dodecagon. All right, I've got it here. It's 24 minus 12 times the square root of 3. I'm going to end up with a square root inside of a square root. So the best I can do is I'm just going to multiply this out. 3 times 24 is 72 minus 36 times the square root of 3. And I'm going to take the square root of that. And that will give me approximately 3.1058. So I know that the circumference of that circle, which we know is pi, is somewhere between 3.1058 and 3.2154. Okay? Well, Archimedes knew that he would get a closer value to the circumference, which he knew was going to be a constant, if he just kept doubling. So he went ahead and used little p sub 12 and capital P sub 12 to find the corresponding perimeters for the 24-sided polygons. Then he found the 48-sided polygons. And then using n equals 48, he found the 96-sided polygons. So for a 96-sided polygon, he found, and at the previous step, he started to use it. He recognized that the circumference was between two fractions. So he used two fractions here, and he found out that the circumference was between 3 1/7 and 3 10/71. Okay, now look at that. That's let me write it like this. 1/7 is the same thing as 10/70. So it's easy to see why he's got it between those two fractions. 10/71 and 10/70. 10/71 is smaller than 10/70. So naturally my inequality goes that way. Now 3 10/70 is 3 1/7, which is 22/7. And that's that Archimedean value that we mentioned before. Okay. Now in your homework, I asked you to do some problems related to some of the other problems that Archimedes worked on. And he actually had proofs for some of those. What I'm just asking you to do is verify that his propositions are true based on the formulas that we know today. So I'm going to talk about that in a different lecture, but this is actually the end of Archimedes. This was the last problem I wanted to look at, and this is probably the problem that he is most famous for, approximating the circumference of the circle, which gives him an approximation for pi. And then also, remember in an earlier that earlier lecture, I mentioned the apothem of this triangle right here. And apothem is the distance from the center of the circle to the midpoint of the opposite side. And that apothem is going to be the perpendicular line drawn from the center to the circle, to the base of that triangle, which is the side of the polygon. That apothem would be used if we were trying to find the area of that polygon, and it was also used when we found the perimeter of that polygon. Okay? All right, so that's the end of this lecture and the end of what we're covering with Archimedes. The next one is on Eratosthenes, and then we will finish with Hypatia. So they're coming up.